Okay, so I have started recording. So we will continue from where we left last time. Last time we discussed infinite products, and the reason for us discussing infinite products was to discuss Weierstrass factorization theorem, or the Weierstrass theorem, which is about constructing holomorphic functions with a prescribed set of zeros. And a very important corollary, which since we have stated it so many times verbally, I have not included in the slides today. Of the theorem. So once again, I am saying it in words. It will not come in the slides. It is that the ring of holomorphic functions, that's an integral domain, and its quotient field is the field of meromorphic functions. And we saw last time why it's a corollary to the Weierstrass theorem. So today we will prove the Weierstrass theorem. So let me share the screen. Please confirm, one of you, that you can see.
Yeah, I can see.
Yeah. So let's start. Today we will do Weierstrass theorem. I hope the spelling is correct. It is correct. So last time we discussed infinite products, but there's only one result which is important for us, which is that a certain product is uniformly convergent on compact sets, and hence it's a holomorphic function. We can conclude if we know something about a certain sum being uniformly convergent on a certain series being uniformly convergent on compact subsets. So when we discuss today certain products, what we will check is the corresponding infinite sum. We will do the checking and then appeal to this result that we did last time and conclude that the product is uniformly convergent on compact sets. That's how we will use those. So let me just restate that result. So last time we saw that if fn's are holomorphic, then this product, an infinite product, this is uniformly convergent on compact subsets, provided what should be given to us. It was if summation un something is given, then product 1 plus un you are concluding. So 1 minus fn. So modulus of 1 minus fn summation, this is uniformly convergent on compact subsets. So this we proved last time. Okay. And this is all that we need for today. And moreover, we know the multiplicity of f at S0, it is the sum of the multiplicities of the individual functions. So today we will do the Weierstrass theorem making use of this result. So the main point is certain functions that Weierstrass introduced, what are called Weierstrass elementary factors. So how are they defined? So for each p, 1, 2, 3, etc., you define EPZ to be 1 minus z times exponential of this much, z plus etc., z power p by p. So this makes sense for p equal to 1, 2, etc. And is there a 0 for this function? There's an obvious 0 for this function, which is z equal to 1. Is there any other 0 for this function?
No.
No, because exponential is never 0. So these are holomorphic functions, nice functions. And we need E0 also. E0 is just 1 minus z. So once again, z equal to 1 is the only 0. So here are a number of functions. For each number, each natural number, there is an elementary factor which has the property. It's defined in this particular way, and this has the property that z equal to 1 is a 0 and there's no other 0. And we will be taking, infinite products of these kind of factors to prove what we want. So our first claim is that if mod z is less than or equal to 1, then modulus of 1 minus EPZ is less than or equal to mod z power p plus 1. We are going to use this later. See, finally, how will we prove that infinite products are holomorphic, etc. The corresponding infinite sum, you need convergence. So you will need some estimates. So this is the first estimate. Why is this true? This is easy. So this is a small check that you do. You just differentiate this thing. So when p equal to 0, there's nothing to prove, right? It's obvious, right? Because 1 minus E0z is just z. So it is equal to mod z everywhere. So there's nothing to prove. So we can assume that p is not 0. In which case you check this. You just take derivative, apply a product rule, and take the derivative, and notice that minus epz prime is the same thing times z power p. So this is a simple check that you should do. I'm skipping it. So do this. So what is the conclusion? Z equal to 0 is a 0 of order p, and there's no other 0 here. And therefore, so this has a 0 of order p at z equal to 0. Therefore, if you consider the function 1 minus epz, you can conclude that it has a 0 at z equal to 0 of order p plus 1, right? If this function is f of z, then z equal to 1 is z equal to yeah, so wrong argument. The correct argument I did not copy. I put the wrong argument maybe. Oh, no, fine. Correct only. Yeah. So I got confused. So 1 minus EPZ is z equal to 0 is 0. What is EP of 0? EP of 0 is, this is 0. So exponential of 0 is 1 and 1 minus 0 is 1. So EP of 0 is 1, right? And therefore 1 minus EP of 0 is 0. So it has a 0 at z equal to 0. Right? This has a 0 at z equal to 0. Now you want to check what is the multiplicity, and the claim is it is p plus 1. Why is that? Because its derivative, this function, its derivative is this, and the derivative has a 0 of order p. So enough number of derivatives vanish, therefore it has a 0 of order p plus 1. Right? So this we have, and therefore we naturally consider 1 minus epz by z power p plus 1. So this has a 0 of order p plus 1. So divided by z power p plus 1 will have a will have no further 0 at z equal to 0, because the maximum 0 is taken out. Okay. And the thing to observe is that when you write this as a power series, what can you say about the coefficients? So the coefficients of the power series, that corresponds to coefficients of the power series for this. But EPZ, if you expand, you have the power series for exponential, and you substitute and do the power series, right? So what you observe is, yeah, you are doing it for 1 minus EPZ. So what you need to observe is that all the coefficients are positive, non-negative. So it just comes from this thing. So 1 minus EPZ if you take, and if you expand it as a power series, all the coefficients are non-negative. So they are real numbers and they are non-negative. Okay, so this also you check, because EPZ is given, no? I mean, it's an explicit power series. So from that you can check this, and then you are done, because modulus of this, so this is some summation a n z power n, so it will be less than or equal to summation mod a n mod z power n. So if mod z is less than or equal to 1, then it is summation a n, because mod a n is a n. And what is summation a n? Summation a n is just phi of 1. And what is phi of 1? Phi of 1 is EP of 1 is 0 and this is 1, so phi of 1 is 1. So you're getting mod phi z less than or equal to 1, and that's what you wanted to prove. You wanted to prove that modulus of 1 minus EPZ is less than or equal to mod z power p plus 1 if mod z is less than or equal to 1, and that you are done. So this is simple computation. So indeed it follows from this, and summation mod a n is exactly phi of 1, and phi of 1 is 1. Okay, so you've got mod z less than or equal to 1, 1 minus the elementary factor, its modulus is bounded by mod z power p plus 1 for the pth elementary factor. Okay, so let's proceed. So now suppose you have a sequence of complex numbers Zn, and none of them is 0. And suppose the modulus goes to infinity as n goes to infinity. So you have a sequence of complex numbers whose absolute value goes to infinity, diverges, and none of them is 0. And suppose you have natural numbers Pn, non-negative numbers, natural numbers Pn, such that such a summation is convergent for every R positive. So whatever R you take, summation n going from 1 to infinity R by mod Zn power 1 plus Pn. Such natural numbers exist. Suppose that is given to you. And then you want to say something about product of elementary factors, but observe that such a thing is always true. I mean, such Pns certainly exist. For example, if Pn is n minus 1, this is certainly true. So there are, you can always get such Pns. Here is one particular example. Why, when Pn is n minus 1, this is convergent? Why is this convergent when Pn is n minus 1? When Pn is n minus 1, this is 1 plus n minus 1, so this is n. So it is R by mod Zn power n. And take whatever R, so fix an R. Now R by mod Zn is going to infinity. So beyond a stage, R by mod Zn is less than 1. And even beyond a stage, R by mod Zn is less than, say, half or 1 by 3, whatever you want, right? Less than a C, which is strictly less than 1. So from that stage onwards, it will be summation C power n, where C is strictly less than 1, and that's a geometric series that's convergent. And the rest is all finite sums. So this convergence is certainly true when Pn is n minus 1, and there may be various other Pns also where it is true. So suppose Pns are such that this is finite, this is a convergent sum for every R positive. Okay, assume that. Now we are going to take a certain product and we are going to conclude that it's an entire function. So fix an R, and for mod z less than or equal to R, consider 1 minus EPN of z by zn. So what do you know about this modulus? What did we prove just in the last slide? 1 minus EPZ, its modulus is less than or equal to mod z power p plus 1 when mod z is less than or equal to 1. So by applying the same thing here, you will get that this is less than or equal to mod z by zn power 1 plus p. P is Pn, 1 plus Pn. Where will this be true? This will be true in the region mod z by Zn is less than or equal to 1. So this will be true whenever mod z is less than or equal to mod Zn. And that is true, no? Because mod Zn is going to infinity. So beyond a stage, that is always true. So beyond a stage, that is always true. So you do get this for almost all n. And mod z is less than or equal to R. Therefore, this is less than or equal to R by mod Zn power 1 plus Pn. And this is true whenever R is less than or equal to mod Zn. And that is the case for almost all n, because you know that mod Zn is going to infinity. So, and you know that this particular sum is finite. This is your assumption. This particular sum is finite. And therefore, if you sum over this, that is finite. Right? Sum n going from 1 to infinity, modulus of this is finite. So what is your conclusion? This is the kind of sum that you wanted, right? In order to show that a certain product converges. So from this you get the feeling, and you can carefully check that this product is going to be good. This is going to be holomorphic. In fact, it's going to be entire, because for any R, for any fixed R, this is true. So whatever, you can increase the radius of your disk, and everywhere it's holomorphic, so it's going to be entire. And this will have a zero where EPN has 0 exactly at z equal to 1. So z by zn equal to 1 meaning zn equal to z. So at each zn it has a 0 and it has no other 0. Right? Therefore, this product, you are in that result, you also know that the product has a 0 if and only one of them has a 0. So P will have a 0 precisely at Zn and nowhere else. So you are constructing functions with prescribed zeros and no other 0 in C. Clear? Right? What you wanted was, in order to conclude that this has all these properties, what you wanted was summation 1 minus EPN Z by Zn should be uniformly convergent on compact subsets. That's what you wanted. And you are getting that from this inequality. Okay, therefore, this is uniformly convergent on compact subsets. And therefore, since all of this are these are holomorphic, this is holomorphic, and that is true for any R. You can increase R, so it's entire. Okay, so this Weierstrass elementary factors, if you take infinite products with those, they behave well. They are entire. So now let f be any entire function, and you're going to show that it has a Weierstrass factorization, meaning it can be written as a product of elementary factors. So any entire function can be factorized as a product of elementary factors. So what you do is, if it has a 0 at z equal to 0, see, we are going to apply the previous result and we wanted Zn to be non-zero here, right? We wanted Zn to be non-zero. Why? Because we are taking z by Zn. We are taking z by Zn, so we wanted Zn to be non-zero. So assume that, so if it has a 0 at z equal to 0, take away the zeros. If it is coming with multiplicity k, consider the function hz is fz by z power k, so that its h of 0 is not 0. Okay, and suppose these are the zeros of h. So you have been given an entire function. You have constructed this entire function which has no 0 at 0. And suppose these are the zeros of h. So the first observation is no zn is 0. Because h has no 0 at 0. So Zn is not 0. And the next question, so you want to apply the previous result. If you have a sequence Zn such that Zn is non-zero and mod Zn goes to infinity, then you can consider those elementary factors. So is it true that mod Zn goes to infinity as n goes to infinity? What do you say?
Here we are assuming that we have infinitely many zeros, right?
Here you are assuming that you have infinitely many zeros. Yes. Yes.
Okay.
Then is
Then
it?
we can say that.
Yeah. Why?
Because otherwise it would have to be bounded.
Yeah, and therefore there will be a limit point.
Yeah.
Yeah. So yeah. So yeah, you are assuming there are infinitely many zeros, and then it has to go to infinity. So I should have written that. I haven't written that. Okay. We will see what happens if there are not infinitely many zeros at the very end. So the answer is yes, and therefore you know that there exists Pn such that this product makes sense. This product is entire. Right. This is what we did last time. Once you have a sequence, none of them is 0 and mod Zn goes to infinity, then this makes sense. This is entire with Zn as its only zeros. Right? So with Zn as its only zeros. So if there are only finitely many zeros, if the function has only finitely many zeros, then you will get a finite product. So you don't need to do this analysis. So even then this statement is true. So whether Zn is finite or infinite, this is true. This is entire with Zn as its only zeros. So the entire function h by p. So what is h? H is this function. Zi's are the zeros of h. And this is another entire function. ZISR is precisely its zero. So when you consider H by P, what can you say? H by P has no zeros. Right? H by P has no zeros. All the zeros are getting cancelled. And H by P is also entire, right? Because it has no poles. Why it has no poles? Because all the zeros of P are getting cancelled. So H by P has no zeros and it is non-vanishing. And if it is non-vanishing, what can you say? You can say that.
Wait, why does H by P have no zeros? In the orders could be different, right?
No, so we are going to say that with the same order, right? So here repetitions are allowed.
Okay.
Yeah, here repetitions are allowed, and therefore it's coming with the same order, right? Assume that repetitions are allowed here. Okay, so if H has a 0 at Z2 of some order, then maybe that Z2, Z3, Z4, etc. is Z2 only. So repetitions are allowed. So precisely the zeros are coming with the correct multiplicity for P also. So when you take H by P, all the zeros are getting cancelled. So it is non-vanishing. That's okay, no?
Yeah.
Yeah. So it is non-vanishing, and therefore you conclude that it admits a holomorphic logarithm. Why? A non-vanishing entire function has a holomorphic logarithm.
Because C is simply connected.
Because C is simply connected. So let's call it G. So what is the meaning of this? That means H by P equal to e power G, exponential of G, because C is simply connected. Therefore, you can write Fz as Z power K times Hz, and Hz is Pz times e power Gz. So this is what is called the Weierstrass factorization. So given any entire function, it can be written as a product of this form. The zeros at 0 you take away with the correct multiplicity. Then all other zeros you put the elementary factors. And then there is a non-zero term where it may be some other entire function. So it is e power Gz. So we are not saying much more about this Gz for now, but at least the zeros are in terms of elementary factors. So this is called Weierstrass factorization. So there's another chapter in Rudin where some of these things are Rudin or Conway, I forget. There is a concept of entire functions of finite order. It depends on this Gz. If Gz is like a polynomial of order n, then that is kind of the order of the entire function. But we may not have time to do those things because I would like to skip that and go to another topic since we don't have so much time left. But say now there's a involving Weierstrass factorization. But what I am planning to do is to give some taste of various aspects of complex analysis. So we may not get into those things. Okay. So this is okay, and now we will do one more thing, and then we will stop. So today also we may stop a bit early. The next thing that we will do is, I'm not assuming that I'm not talking about entire functions. My domain need not be the whole of C, but I will consider S2. That makes the proof somewhat easier. Instead of considering C, I'm going to consider C union infinity and take an open subset of S2, which is not the whole of S2. Okay, so take a proper subset, which is an open subset. And suppose A is a subset of omega without a limit point in omega. And associated to each point in A, you can also give me a number which is going to be the multiplicity of the zero. And now we have to construct a holomorphic function, a function holomorphic on omega, whose zero set is precisely A. And to associate it to an alpha in A, if you have given me M alpha, then the multiplicity of the zero is precisely M alpha. So the idea is, so this is the Weierstrass theorem. We want to show that if you give me a set and if you give me prescribed multiplicities, I can construct a holomorphic function whose zeros are precisely the set that you have given, and the multiplicities are precisely the multiplicities that you have given. So suppose A is without a limit point, and so one thing that we might have used earlier also, I forget, but anyway, this is true, that so what is a Mobius transformation? These are transformations of the form Az plus B by Cz plus D. When you were doing automorphisms of the disk, open unit disk, we have seen that particular kinds of Mobius transformations are precisely the automorphisms. And for S2, the automorphisms are all Mobius transformations. So using an automorphism of S2 if necessary, you may assume that infinity is in omega, this set omega, and infinity is not in A. So what you can do is, if that is not the case, you apply a Mobius apply your automorphism of S2, apply a Mobius transformation, and do the shifting. So take a point in omega and map it to infinity, and take a point in omega which is outside A and map it to infinity using a Mobius transformation. So you will get infinity belongs to omega and infinity is not part of your set A. So omega is open set, so S2 minus omega is not whole of S2, so this is non-empty. S2 minus omega is non-empty, and S2 minus omega is compact. S2 minus omega is compact because omega is open in S2, so S2 minus omega is a closed subset of S2, and S2 is compact, so this is compact, but it's a compact subset of C. Why? Because infinity is in omega, so infinity is not part of S2 minus omega. So S2 minus omega is compact, and it is actually a compact subset of C because infinity is not there. And you also know that infinity is not a limit point of A. Why? Why is this sentence true? Infinity is not a limit point of A. Because
A has no limit points in omega.
A has no limit point in omega, and infinity belongs to omega. Therefore, infinity is not a limit point of A. Okay, so this is what you have. You have, by your assumptions, which is a without loss of generality assumption using a Mobius transformation, you have got S2 minus omega is a compact subset and infinity is not a limit point of A. Now we are going to claim that there exists f in h omega, holomorphic function on omega with zero set of f as precisely A. Moreover, multiplicities can be prescribed. So what is the meaning of this? Associated to alpha in A, if there is a number m alpha which you have given, I'm going to claim that f as a zero at alpha of multiplicity of order m alpha is going to be the claim. So if A is finite, then there's nothing much to do. If A is a finite set, then what will you do? You want
Polynomial.
Polynomial is the word, because infinity is, yeah, so infinite. Yeah, it's a polynomial. So what do we want? So we have omega is, infinity belongs to omega, right? So it is,
yeah.
It is holomorphic in omega. So it need not be a usual polynomial. It's polynomials in this sense. I mean, your domain contains infinity also. So the word is
Rational function.
rational function. Yeah, polynomial. That's correct. So rational function. So if A is finite, then we can take an appropriate rational function, and there's nothing more to do. So you can assume that A is infinite. You can assume that A is infinite, and then A has to be countable, right? Why is that?
Because A has no limit points.
Because A has no limit point. So it is certainly countable. So we are going to construct this sequence alpha n, where I am going to take the multiplicity into account. I will repeat if necessary. So these are precisely the elements of A. It's a countable set, and associated to each element you have given me a multiplicity. So one alpha, if I take, I'll repeat it that many times. So this sequence will have repetitions, precise repetitions, okay, whose terms are in A, and each alpha in A is listed precisely as per its prescribed multiplicity that you have given me. So that's the sequence. So this is the sequence of zeros. So now we are going to take certain elementary factors so that the zeros will be precisely alpha n's. That's enough, no? Because multiplicities are accounted here because I'm repeating alpha n's. Okay, so to each alpha n, now we are going to construct a certain elementary factor. We will use EP, but inside the bracket I should put proper things so that I get alpha n as the zeros. Okay, so one small thing we have to do, and that's what we are doing now. First, observe that to each alpha n, we can find the beta n in S2 minus omega, which minimizes this distance. Mod beta n minus alpha n, the distance from alpha n is minimized over S2 minus omega, right? Alpha n is where? Alpha n is in A. So alpha n is in omega and beta n is in S2 minus omega. So you fix an alpha n, and then the claim is associated to that alpha n, there is a beta n which minimizes this distance, beta minus alpha n modulus. Why is this true? Why should there be such a beta n?
Because S2 minus C is compact.
2 minus omega is compact. So you can take the minimum of mod beta minus alpha n over S2 minus omega, and that minimum is attained because S2 minus omega is compact. Okay, so that minimum you call it beta n. Right. So minimum is attained precisely once, or doesn't matter for us. One of those you can call beta n, but is the minimum going to be unique?
No, not necessarily.
Yeah, not necessary, and we don't need it. So take one of those and call it beta n. Okay. So this is S2 minus omega being compact. So keep that in mind. And next observation is that beta n minus alpha n, this modulus goes to 0 as n goes to infinity. So you have got such beta n, and then the claim is this goes to 0 as n goes to infinity. So why is that? So you can keep a picture in mind. So S2 minus omega is a certain compact set in C. So visualize, something like a unit disk or something, a compact set in C. And where are alpha n's? Alpha n's are outside that. And beta n is in S2 minus omega. So beta n is part of this compact set. So in this picture, beta n's are on the boundary, right? Because it is minimizing the distance. So if beta n was inside, the distance would have been more. So beta n is like in the boundary. And now you are saying as n goes to infinity, this distance beta n minus alpha n, that goes to 0. So what will happen if that is not the case? So you will get this.
A would have the limit point.
Yeah, it will have a limit point because this sequence alpha n, it is not really hitting the boundary of S2 minus omega. It will stop somewhere else, which means you could have considered a compact set in which all these infinitely many alpha n's will belong, right? You can go a little bit above the boundary, and you can above the boundary of S2 minus omega, and you will get a compact set there where all alpha n's will belong, and then it will have a limit point. So you conclude that this distance actually goes to 0 as n goes to infinity, because otherwise you will have an infinite sequence in some compact subset, suitable compact set inside omega, and that will be a contradiction because then a will have a limit point. So this going to 0 is useful, and we are going to consider. So the claim is that you consider these elementary factors. See, finally we are going to take products of elementary factors, but what is the what is there in the bracket. So we are going to take alpha n minus beta n, which goes to 0, by z minus beta n. So what will be a 0 of this? A 0 of an elementary factor is precisely when the inside the bracket thing is 1. So alpha n minus beta n equal to z minus beta n. So that means z equal to alpha n are precisely the 0. Z equal to alpha n is precisely the 0 of this En. And therefore alpha n's will be precisely the zeros of f and nothing else will be there, because our theorem says that a 0 of this is precisely a 0 of one of this. So and alpha n's are repeated correctly with the correct multiplicity. Therefore this will do the job. Okay, so we just have to, what do we need to show now? We need to show that this makes sense. This makes sense. So in order to show that this makes sense, this is uniformly convergent on compact subsets. What do we need to show? We need to show that summation 1 minus En, summation modulus of 1 minus En of this, that has correct good properties. And that's easy. So let's do that. So we are going to take twice alpha n minus beta n, you call it Rn, and you take a compact subset. And what do I need to show? I need to show that 1 minus En of that thing modulus summation that is uniformly convergent on K. That's what we need to show. So there exists some capital N such that mod Z minus beta n is bigger than Rn. Why is that true? For all Z in K and for all n bigger than or equal to n. Why is this true? What you know about Rn is that alpha n minus beta n we have already claimed, right? Alpha n minus beta n goes to 0. So Rn goes to 0. Rn goes to 0. So beyond a stage, Rn is very small. So mod Z minus beta n can be made to be bigger than Rn, and this can be done for all Z in K. Where are beta n's from?
Beta n are outside K, right? Outside omega.
Yeah. Beta n is in S2 minus omega. Beta n is in S2 minus omega. So beta n is outside omega, therefore outside K.
So the distance of beta n from K is some fixed positive point.
That's a fixed constant, and beyond a stage, Rn is small enough, and therefore this is true. So this is because Rn goes to 0. Right? Z minus beta n is a positive number, a fixed constant, and Rn goes to 0. So this is true beyond a stage for all Z in K uniformly. Okay, and which means alpha n minus beta n by Z minus beta n is less than or equal to half. That was your definition of Rn, twice this, and that's all that you need. And therefore, for Z in K and for n bigger than or equal to n, 1 minus this quantity is less than or equal to, no, there's a typo here. I missed the, what is missing here? En. 1 minus En of this thing. We know that 1 minus EPZ is less than or equal to mod Z power P plus 1. So there is an En here. So 1 minus En of this is less than or equal to modulus of this power n plus 1. And modulus of this is less than or equal to half. So this is less than or equal to half power n plus 1 whenever mod Z is less than or equal to 1. So whenever modulus of this is less than or equal to 1. And but we are taking modulus of this is less than or equal to half. So this is certainly true. Whenever this is less than or equal to 1, this would have been less than this power n plus 1. But you are considering this is less than or equal to half, so that is certainly applicable. So this is less than or equal to half power n plus 1, and therefore summation half n plus 1 summation this is convergent. For fz as this product, this is uniformly convergent on K, and this is true for any K compact. So this is uniformly convergent on any compact subset, and therefore it's a holomorphic function. It is holomorphic in omega, and all the properties are there because our theorem also says that the zeros of f has a zero at z0 precisely when one of this has a zero at z0, and the zero of En is precisely alpha, and there's no other zero. So all the other desired properties are there. So this is the proof of Weierstrass theorem. So proof is easy. It's just some basics on infinite products, and so the ingenuity here is Weierstrass thought of these elementary factors and notice these basic properties of elementary factors, and you can take infinite product of these elementary factors. Holomorphy is not lost, and that will do the job. Okay, so it's a beautiful theorem, and the corollary that is not part of the slide says. If you have the ring of holomorphic functions, it's quotient field. So typically we say quotient field for an integral domain, which is true. So it's an integral domain of holomorphic functions, and its quotient field is actually for ring also there's a notion of quotient field, but then you need some equivalence to define the quotient field. Whereas for an integral domain, you can just take f by g. Otherwise, if zero devices are there, you need to define it a bit more carefully. Anyway, this is an integral domain, and you have the quotient field, and the quotient field is the field of meromorphic functions. And what was the proof once again? If you have any meromorphic function, take its set of poles and construct a holomorphic function with zeros precisely those poles, and take f times g, and that is holomorphic. Now f g by g. So you need this theorem in order to conclude that. Okay, so let's stop here. We will stop the recording and start the new recording.